This is the last question from the sample exam. This is our velocity selector problem. In this question, we have a charge of minus 2.5 nanocoulombs. It's accelerated through a capacitor with a potential difference of 1,000 volts. Then it goes through what's called a velocity selector. It has both electric and magnetic fields, and it goes straight on through. Then finally, it enters a third magnetic field. The entire system is shown here in this picture. We're told to assume that we can always neglect the force due to gravity in this problem. Question 33. Show the charge on the capacitor plates and the direction of the electric field for section A. What we know about electric field is that it points from high potential to low potential. We can use that to draw our electric field. So to go from high to low, we'll go from 1,000 down to 0. There's our electric field. We also know it also points from positive to negative. So now we can label our plates as positively charged and negatively charged. Okay, question 34. Find the magnitude of the electric field between the plates in volts per meter. Here we remember that the magnitude of the electric field is the magnitude of the potential difference divided by the distance between the two plates. So our potential difference is 1,000 minus 0. The distance between the two plates is given in the picture, 0.625 centimeters or times 10 to the minus 2 meters. That gives us an electric field magnitude of 1.60 times 10 to the 5 volts per meter. Okay, so that's our first couple of questions. Let's see what's coming next. In question 35, it asks, true or false? When we release a charge from rest in an electric field, it will always move towards lower potential energy. That is definitely true. And that's what objects do. If we release them from rest, they'll go towards lower potential energy. Question 36. The charged particle is released from rest at the 0 volt plate. So we start here. The velocity is initially 0. Find the speed when it reaches the 1,000 volt plate. So it accelerates over to this side and it has some final speed that we'd like to figure out. Let's give that one a question mark. There are two different ways to do it. You could certainly do this using kinematics. Use the field to find the force, use the force to find the acceleration, and then use your kinematics to find the speed. I think I'm going to use an energy approach. I'll say at the 0 volt plate, it's my initial. At my 1,000 volt plate, that's my final, and I know that my final mechanical energy is my initial mechanical energy plus work done by any non-conservative forces. We don't have any friction or anything like that, so the work done by non-conservative forces is 0. My final mechanical energy is Kf plus UEF. That's equal to my initial mechanical energy, Ki plus UEI. Let's see what I have for each of those terms. Kf is 1/2 times m times the final velocity squared. I called that v. UEF is my charge Q times my final potential. That's my 1,000 volts. Ki is 1/2 times m times vi squared. Vi is 0, so my initial kinetic is 0. UE initial is my charge times my initial potential. My initial potential is equal to 0, so my initial potential energy is equal to 0. So this term is 0 and this term is 0. Kf is 1/2 times m times v squared plus UEF is q times vf. And that's going to give us 0. I'm trying to solve for my final velocity here. Be really careful with your signs in this problem. If you get them mixed up, you could end up with a negative underneath the square root sign. So now v squared is going to be minus 2 times q times final potential divided by mass. To find my v, I'll have to take the square root. Let's put our numbers in. Square root of minus 2. Our charge is minus 2.50 times 10 to the minus 9 coulombs. Final potential is 1,000 volts. Divide that by the mass. The mass was 1 microgram. Micro means times 10 to the minus 6, and a gram is 10 to the minus 3 kilograms. So 1 microgram is 10 to the minus 9 kilograms. That gives us a final speed of 70.7 meters per second. We'll notice that inside we had a negative times a negative, so we did have a positive value inside our square root, which was good. All right, next question takes us to section B. In section B, it says draw the free body diagram of the charged particle in section B. Reminder, the charge moves straight through this section with constant velocity. If our velocity is constant, then that tells me that the acceleration is constant, and that makes me think that the sum of my forces, which is mass times acceleration, is also 0. So if I'm thinking about my forces, I know there's an electric field and a magnetic field. That tells me there's going to be a magnetic force and an electric force, and when I add those two forces together, that's going to have to give me 0. This tells me that my electric force and my magnetic force must have equal magnitudes and opposite directions. That's how you get them to sum to 0. They have to be equal and opposite. Okay, let's start with thinking about the electric force. My charge is negative, my electric field points up, and I remember that electric force is charge times electric field. If my charge is negative, then my force and field have opposite directions. My field is up, so my electric force is down. Now I come back to this idea. My electric force and my magnetic force have to have opposite directions. If electric force is down, the magnetic force must be up. Okay, so there's our free body diagram. Next, find the magnitude of the magnetic force on the particle while it's in the field. Well, let's deal with the equal part next. I've said that they must have equal magnitudes, so the magnitude of the magnetic force is equal to the magnitude of the electric force, and I know that that's equal to the magnitude of the charge times the magnitude of the field. The magnitude of my charge is 2.5 times 10 to the minus 9 coulombs. Remember, magnitude means take the positive value. Multiply that by the electric field. That's given us 3,500 newtons per coulomb. And I get a force of 8.75 times 10 to the minus 6 newtons. So there's the size of the magnetic force and the electric force. Next, what's the direction of the magnetic field in section B? Well, we've established that the direction of the magnetic force is up. So we know the force, we know the velocity. This gets us thinking about our right-hand rule. And remember, this is for a positive charge. Velocity is the direction that you point your fingers. B is the direction that you bend your fingers towards. And magnetic force is what you get when you stick out your thumb. Let's try that here. So if I point my fingers towards V, and then I bend them into the page, I see that my stuck out thumb is up, which does match this question. However, I have a negative charge. My force would be up if my magnetic field is into the page on a positive charge. Because I have a negative charge, my field can't be into the page. It must be out of the page. So I point my fingers to the right, I stick my thumb up, that matches V and B. When I bend my fingers, it's into the page. That would be the direction if this were a positive charge, but it's not positive, we have negative, so we have to flip it. The direction is out of the page. All right, now let's find the magnitude of the magnetic field. Let's remember that the magnitude of the magnetic force is the size of the charge times the size of the velocity times B times sine of the angle between V and B. V is to the right, B is out of the page. The angle between them is 90 degrees. Here it says use a value of V of 100 meters per second. That's just in case you got the previous question wrong. We didn't want this answer to be wrong as well. Okay, so sine 90 is equal to 1. B is going to be the magnitude of the force divided by the magnitude of the charge times the speed. 8.75 times 10 to the minus 6 newtons divided by 2.5 times 10 to the minus 9 coulombs times 100 meters per second to get a field of 35 teslas. Okay, question 41. In the third section, the charged particle enters the magnetic field which points into the screen and has a magnitude of 125 teslas. What path does it follow? So our charge starts here at rest, it accelerates until it gets right here, moves through this region with constant velocity. Then when it gets here, it's moving to the right with that same constant velocity. To think about the path, let's figure out what's the direction of the force. Our right-hand rule says you point your fingers with velocity, bend them towards B. Your stuck-out thumb is your force on a positive charge. This one is negative, so it has to be opposite. The force on this charge is down. Here we have a force perpendicular to a velocity. That means we have circular motion, so it's going to go around in a circle like this. So there's the path that it's going to follow. Question 42, find the radius of that path. Well, to find the radius of the path, let's write down Newton's second law. Sum of the forces is mass times acceleration. Remember, we were told we could ignore gravity. So the only force is the magnetic force. That's equal to mass times acceleration. So we have Q times V times B times the sine of the angle between the velocity and the magnetic field to the right and into the page. That's 90 degrees. Whenever something goes in a circle, instead of A, we say V squared over R. And we notice that one of our V's cancel. Sine 90 is 1. Let's solve for R. That's going to be M times V divided by Q times B. So our mass was our 1 microgram, 1 times 10 to the minus 9 kilograms, times our V, again told to use that 100 meters per second, divided by the magnitude of the charge, divided by B, 125 teslas, gives us a radius of 0.32 meters or 32 centimeters.